Hello and welcome to episode 3, sorry, of Multivariable Physics. And today we're going to be talking about derivatives, and specifically derivatives of multivariable functions. I'm going to be moving at a bit of a faster pace since I've been going kind of slow and I don't have all the time in the world. So I'm going to try to pump out as many of these as I can. So the first thing we want to do, okay, is, well, we want to let's just graph, for example, just this f of x and f of y, right? Here's our function f, and we're going to create a graph. Okay, so we have already talked about that these graphs kind of form these surfaces, right? We can form these kind of surfaces with these graphs. So let's think about what it means to take a derivative here. So if you remember from calculus, you have this intuition. We have this graph x and f of x, right? You have some curve, and what you're doing is you're taking some let me go back. You're taking some tiny step, so from some x to x plus dx, okay? And then your function is going to take some step, f of x plus dx. And I'm sorry for the tiny text, but you should be familiar with this, right? So the idea here is very similar, except now we have two parameters. So what we need to do is we need to think about one tiny step here, okay, in the x and in the y. So we think of one tiny step, x plus dx, and f of x plus dx, and a tiny step, y plus dx, and f of y plus dx. And then obviously we have x just not moving, and then in this example we actually just have y is not moving. Right, so this is going to give us, we have two values here and they're obviously independent of each other, right? When y is moving, it's not moving in x when it's moving in y, right? So we get two vectors out of this, and what we can do is we can actually combine these vectors by adding, if we add purple here, we add some green, we end up getting this vector here. I'm going to talk about what that vector is, but first let's actually kind of write down this these limits, and this is going to be the limit as h approaches 0, sorry, of f of x of y plus h minus f of x y over h. And then we have in green we have this limit as h approaches 0 of f of x plus h y over h of, or minus f of x y. Okay, and so we call these are basically derivatives, but they're derivatives in one variable only, right? So these are called partial derivatives. So this is actually, it's written like this with these funny d's. These are d's, these are deltas. Partial f, partial x is what that is referring to, okay? And then this is obviously the partial derivative in f or the partial derivative in x. And obviously we mentioned that these are vectors, right? It's because they point in different directions. So what happens when we combine them? So we have some vector v, which is equal to, and then also this is going to, so for simplicity's sake, actually these are written like this. And then equals f of y. This is supposed to be a y. Apologies, right? So what happens if we take f of x plus f of y, right? What do we get? And so, well, this is obviously these are independent vectors, right? So we get another vector. So this is going to be some vectors. Just I'm going to make that a little closer. It's just this vector here with f of x, or partial in x, partial in y, right? And this is called the gradient. This is the gradient vector to f. That's what that is at that, all right? And so this is some point A. The vector is this vector here in particular is the gradient of f at f of x at f equals a. So there's a shorthand for this, and we use, so there's a few words, nabla, del. These are two words for it, but we use this funky symbol here, and we apply that to f, and then that is equal to partial f over partial x, partial f over partial y. That, and so that's all that is. That all that this is saying is we're taking the gradient at f, right, is just the two older partial derivatives, because this also works in however arbitrarily many dimensions we have, right? And that's just a vector that's kind of the sum of all the changes, right? Which direction is it is it moving in, right? And then that'll change for every point. So one interesting thing to kind of notice here is that this nabla actually, well, when we take this gradient, we get some function, it's a scalar function, and then it's going to turn into some function. It's going to turn into something in 3D. So it's actually going to turn into a field almost, where we're going to actually have like different arrows. So it's actually going to turn into almost like a vector field. And right, so we can actually form vector fields from scalar functions. You can form, so this nabla here is it can act as a vector valued function. But there's a catch here. It's not exactly a vector valued function. What we're actually doing here is we're actually taking a vector. We can define this in terms of a vector value function. So I'm going to define a function. So we're going to have define some function. Okay, so we start off actually first defining f takes r n to r. Okay, so we have f of x, and then I'm going to define this function here, g, which takes this function, and so g is defined as a function takes one parameter, and then it spits out a vector. Okay, and then this we can say is simply nabla f at x. We can define nabla in terms of that, but a better way to actually think about this nabla is actually just as the vector partial of these unapplied partial derivatives. This becomes a slightly more useful way to think about the gradient, and you'll see why as we start moving into these and actually looking at the differentiation rules in multiple dimensions. Right? But yeah, if you think about, well, I'll get into exactly the relationship between what happens if we take a scalar function, you take its gradient, now we have a field. Like, what does that mean? We're going to get into that really soon after we talk about the differentiation rules and stuff. So, see you next episode.